Hello and welcome back. Now today I want to look at a topic regarding power distribution, especially in AC power lines. And that is of course looking at the power factor. What it is, what it represents, and more importantly how to simulate it and measure it using LTspice. So if you're curious, then keep watching. Now, to understand the power factor, we need to look at AC current and voltage and how these behave when a generator is supplying a load. So what I got here is my power amplifier, which is supplied from the signal generator, and it's outputting a sine wave at 50 Hz, which is the yellow line, roughly 4 volts peak to peak. And I'm using this voltage coming out this wire to supply a resistive load, so basically a resistor, and at the same time using a 1 ohm shunt resistor and the blue channel, I'm measuring the current flowing through the circuit. And what we can notice, looking at the voltage and the current, is that both of them are sine waves, so this is a linear load, but more importantly, as the voltage rises, so does the current. When the voltage drops, so does the current. So we have a perfectly direct link between the voltage and the current in this circuit. And if we just adjust them a bit, we can see that there's absolutely no phase difference between the two. So when we have a peak voltage, we have a peak current. So nothing really interesting is happening until now. Now on the other hand, if we switch from a resistive load to a reactive load, so either a capacitive or inductive load, like a transformer or a motor or something like that, something interesting happens. So for that purpose, I will be using this transformer, only the secondary side of it, as an inductor. And now if I just adjust these a bit, we will see that something did change. We're still having a sine wave in our current, so it's still roughly a linear load, but the peak current and the peak voltage are no longer aligned. We can see that the current is slightly lagging behind the voltage. And that is because of the way the inductor opposes the flow of current. So one of the properties of an inductor is that it will store energy in the form of a magnetic field, and it will oppose the flow of current. And then when the voltage is dropping, it will give back the stored energy to the system. Now we can better look at this on a still shot. So what I got here is a measurement I've done previously, and we can clearly see the voltage in yellow and the current in blue, and the two are offset one from the other, so we have a phase shift in between the two. And there's some valuable information we can learn from this measurement. So normally, with the resistive load, so the one that we looked at previously, both the voltage and the current have the exact same polarity. So when the voltage is positive, the current is positive. When the voltage is negative, the current is negative. That means that power is flowing from the power supply to the load. Now if we look back at our inductive load, we see that when the voltage turns negative, our current is still positive. So for a brief moment, rather than supplying our load from the generator, we're supplying the generator from the energy stored in our load, so in the magnetic field of the inductor. And we see the same phenomenon happening on both sides. So we have a negative voltage and positive current, and we have positive voltage and negative current. That means that part of the energy that we consume from the generator, we're putting back in. So it's not really being wasted, but all this power needs to travel along the lines. And power factor actually refers to how much of the power that traveled along the line actually gets used up as useful power. So all of this power that just gets stored and then put back in is not really useful. The useful power is only the power that we're taking out from the system. And there's a direct link between how much these two waveforms are shifted and the power factor. So the power factor is the cosine of the phase shift angle. So to figure out what the power factor is, we need to be able to measure this phase shift. So let's look at this in a simulation. So we can start off with this really simple circuit that will mimic what we just saw practically. So I got my 4 volt sine wave running at a frequency of 50 Hz, in series with a 10 ohm load, and the 55 millihenry inductor. So this was roughly the inductance of the transformer I was using. Now if we run this thing, we see our supply voltage and that we do get our phase shift. Now before running through the entire mechanism of how to calculate the power factor, I just want to mention that there's a really easy way of doing this, but before that I will show you the really hard way of doing it. So the first thing we need to do is figure out the phase shift between the two waveforms. And we can calculate this by measuring the time difference between the two peaks of the waveforms. So as long as the voltages are fairly stable, and you can ensure this by setting a time to start saving data larger than 0, so let the simulator run for a while and then start measuring, we can ensure that our signals will be stable. So this is quite useful in general if you want to make measurements. So I prepared a set of measure statements to find this phase difference. So first of all, what I'm doing is measuring the peak voltage first on the supply and then on the current. Now I put a minus in front because LTspice reversed the current, so for whatever reason it's default like this, but that's not a problem. Then I will want to measure the time when the current reaches its peak value, and then measure the time when the voltage reaches its peak value, and these are both in reference to the 0 time from when the measurement is started. Finally, I will measure the time difference between the two, so the delta time, and from there we can work out the phase shift by taking the time difference, multiplying it by the frequency, or dividing it by the period, and then multiplying this by 360, so for degrees. And if we do this, we can see in our error log that the peak voltage was measured at 3.99 volts, so very close to the 4 volts it was supposed to be at. We have a peak current of 200 milliamps, we have the times for the two, we have the time difference, and we have a phase shift of minus 419 degrees. It's a bit too much, isn't it? So the main problem here is that for LTspice the waveforms aren't functions, but rather sets of points. So our peak voltage doesn't happen at every single peak of the waveform, it might happen only on a single peak, because of the way the individual points are measured. So we don't have a very big difference between the peaks, but since the two peaks are not one next to the other, we get this sort of behavior in which our time difference is more than a period. So to correct this, we can add this extra measurement line in which we divide our measurement by 360 and apply the modulo function. So basically to get what is left after the division by 360. And if we do this and look at the results again, well, we get a phase of 300. And the problem with phase shift is that it should be between plus 90 and minus 90. We shouldn't be getting 300. And by applying the modulo function, we cannot get a value that is negative. So we can't get to the minus 90 region. So the final thing to add here is to take our value that we just measured, add 180 and then subtract 180. So that it's no longer centered around 180 but centered around 0. And by applying this modification, if we look at the error log again, we get a phase shift of minus 59. And now from this we can easily move to measuring the power factor. So simply calculate the cosine of this phase shift, which is 0.5, so our circuit has a power factor of 0.5, pretty poor. And now we can also work out the real power, the reactive power, and the apparent power. So the three main types of power in AC. So for the real power, we can simply take the average of the power dissipation on the power supply. So by going with the Alt key over it, left clicking, we get our power dissipation, our power supply, and we can work out that the average is 200 milliwatts. Again, it's negative because of the way LTspice interprets the current. And we can also calculate this by using a measurement statement, by calculating the average of the voltage on the supply times the current going through the supply. Then we can work out the reactive power, that is our real power times the tangent of the phase shift, and we can work out the apparent power either by a trigonometric method using the phase shift or by simply dividing the real power by the power factor. And if we rerun the simulation, we see our 200 milliwatts of real power, so just like we've seen from LTspice directly, we have a reactive power of 340 milliwatts and an apparent power of 400 milliwatts. And normally this method will work for linear loads. So what is a linear load? Well, basically it's a type of load that will not affect the waveforms. So in this case the voltage is a sine wave, the current is a sine wave, so this is a linear load. On the other hand, if you have a circuit like this, so a load like this, so this is quite common to have a rectifying diode supplying a capacitor and then some other circuit. In this case, if we look at the voltage, it's still a sine wave, but the current looks nothing like a sine wave. And in this case, we are talking about a non-linear load. And with this kind of load, we don't just care about the phase shift, we also care about how distorted the current is, since both of these factors have to do with the total power factor of the circuit. Now in this case, the distortion isn't causing power to go back into the power distribution network, but rather it's causing power to be drawn in a non-efficient way. So if you're drawing current like in this circuit only in very brief periods of time, rather than having it spread over a wider time range, so throughout the sine wave, then you will need very thick wires to supply the current, much thicker than if you would have a linear load. So in this case the power factor also has to do with how efficiently we are pulling energy from the lines. Now we could again try to measure the phase shift by looking at the peaks of the waveforms, but in case of a more distorted waveform, so for example here I'm supplying a saturating inductor from my signal generator, we see that the peak of the current isn't really where it's supposed to be because of the way the waveform has been distorted. So a better way to extract the phase shift is to rely on a bit of complex mathematics. What I got here is a set of measure statements that are basically applying a Fourier transform to the set of points forming our waveforms to extract its various frequency contents. And it's doing this to extract both the real and the imaginary part of the function that defines this waveform, and then we can process these functions to extract phase shift. So basically the first 6 lines are extracting the imaginary part and the real part of the voltage and the current, and then in the final line it's using the 4-quadrant arctangent function to determine phase shift and then subtracting one phase shift from the other and basically doing the same thing that we did previously. So if we run this simulation and look at the error log, we can see the new measured statements that we've added. So we see the way in which the real part and the imaginary part are calculated, and finally we get a phase shift of 10.9 degrees, so 11 degrees. But we still need to obtain the distortion. So normally what we could do is apply a force statement to the current. So for example, force statement of the current going through R1 to extract the distortion at 50 Hz. And by doing this we get a distortion of 162% almost. But the problem with doing this is that it won't output the distortion as a parameter, but just as a value in this error log. So to get it as a parameter, to actually perform some calculations with it, we need to calculate it ourselves. So what I did here is a bit more of the complex mathematics we had right above, in which I'm extracting the functions for the current at frequency multiples. So initially we extracted at our base frequency of 50 Hz, and now I'm extracting it at twice that frequency, 3 times and 4 times. You can go on for far more multiples if you really want to. And then I'm calculating the total harmonic distortion by this very nice and long formula. And if we run it and try it out, so we remember that LTspice calculated 162%, and my long method is calculating a value of 143%. So it's a bit less because I'm not looking at all of the spectral contents, but it's close enough. So now finally we can calculate the power factor for a nonlinear load by taking the cosine of the phase and dividing it by the square root of 1 plus the harmonic distortion squared. So we get a power factor of 0.56. And finally we can calculate our real power and apparent power, first of all by taking the average power used from the power supply, and secondly dividing this real power by our calculated power factor. So we got our measurement results here. So it's starting to get quite crowded, and we get a real power of 12.7 milliwatts and an apparent power of 22.58 milliwatts. So I didn't really have a very large load, that's why we're getting such small values. Now remember when I said that there's an easy way to do all of this? So maybe you like it, I'll leave this simulation in the description so you can play around with it. But the easy way to obtain the power factor with nonlinear loads is again to use the for statement. But we already did that, we looked at the current going through a resistor and we didn't really find out anything. But something really interesting happens if we apply the for statement on the current going through a voltage source. So in this case, I'll be applying it on the current going through our initial power supply. And now if we look at the error log, we see the current going through the resistor and it's only telling us about the distortion of the current. But if we look at the current going through the voltage source, it doesn't just give us the distortion, it also gives us the power factor. So taking into account the full complexity of the harmonic distortion, LTspice calculated the power factor of 0.51, whereas we, in a much more complicated way, got a power factor of 0.56. So the two values are very close, the difference is because of the way the harmonics distortion is calculated. Now again, the power factor is not a parameter that you can extract to use in some other calculations, but if you just want to find out the power factor, this is a much easier way. So all in all, whatever circuit you're designing, it's important to have a power factor as high as possible so that you don't waste too much energy on the power lines. And you can figure out the power factor using LTspice, either in the complicated way or the rather simpler way. So the first step is to know your power factor, and the next step is to try to increase it. And I'll be looking at that next time. But for now, hope you got some useful information out of this. Leave your thoughts in the comments, thank you for watching, make sure to subscribe to be up to date with all my latest videos, and see you next time, bye bye!